Okay, cool. Hi, everybody, and welcome to another Machine Learning Dublin remote session meetup. Thanks to Matthew Nicholson for organising it, all the speakers and the logistics. So tonight, first up, we have Hossein Javidnia, who's a postdoc researcher in the ADAPT Centre, and he'll be talking about deep interactive image matching. And then after that, we have Iacer Calixto, and then the last speaker of the evening will be Kamışlı, and she'll be talking about her work with one of the ADAPT startup teams called CaliberAI, and she'll be talking about NLP models for defamation and toxicity. And I should say also, Iacer is going to be talking, it's kind of NLP meets image analysis, I guess. So it's predicted scene graphs for image captioning and whether they're any good for the task. So without further ado, I'm going to hand over to Hossein.
Thanks, Declan.
Cheers.
Good evening, everyone. This is Hossein Javidnia from ADAPT Centre, Trinity College Dublin. Thank you for attending the ML meetup today. I will be talking about deep interactive image matching, one of our recent research that we had a collaboration between ADAPT Centre and Javidnia Group in Trinity College. Just to give a bit of an introductory context on the problem, in general, alpha estimation, we define it as a regression problem where we try to basically calculate the opacity value of the pixels in an image. And by pixels, in this case, we are referring to an object of interest. And an object of interest, mostly in our case, would be a foreground object. We refer to it as a foreground object. And there is a wide range of applications for such technology, mostly on movie post-processing, digital image editing, and video composition. And most of you are familiar with green screen technology, where you basically record a scene on a green screen background, and later you basically remove the background or replace the green background with or a scene from another video. And that technology is based on alpha matching for video processing. In general, the standard flow of such technology is that you basically have one image as an input, and the second input is a guidance map that we refer to it as a tri-map, where the foreground object or the object of interest is marked with the value of 1, the background area opacity value 4. And this is basically a visualization of the classical methods on alpha matching approaches. So you have one image, and then see there is a mask called the tri-map, and that's what we are referring to. So our object of interest, the known area of the object of interest is marked with the value of 1, the background is 0, and then you have a gray area around the mask, and that's the unknown area. And the goal of the matching algorithm is to optimize that area and give us a very fine opacity or segmentation value that follows the structure of the foreground object. And at the end, we get a very fine detail mask, as you can see in this slide. We may be able to refer to it as a segmentation mask, but segmentation usually is known as a mask where the values are binarized between 0 and 1, but in alpha, the value varies between 0 to 1. There are certain problems with the state-of-the-art, but most importantly, most of the state-of-the-art methods, they lack interactivity. One thing that I have to note as well is that the tri-map or the guidance map is a map that has to be created by an artist, or someone has to create such a mask for each individual image. And assuming that if you have a video of, let's say, 60 frames, then someone has to manually draw this mask for each individual frame, or you need to have a technology that allows you to create the mask for one frame and then propagate such a mask across the entire video, and then you can apply the matching algorithm to these videos and get the alpha. And The best performing algorithms in the state of the art, they usually rely on a very tight try-map, meaning that you need to find a very fine details in your object of interest, around the object of interest, and you need to mark that with the unknown area. Time-consuming process, and it's a very exhaustive process. And the state of the art, another problem with the state of the art is that the state of the art does not bridge the gap between the segmentation problem and alpha matching problem. It's covering the binary segmentation problem, and then there are a bunch of other methods covering the matching process. And if you basically give an image for the matching to the segmentation, the method will fail, or for the segmentation to matching, the method will fail, and you won't get any output. So what we are presenting here today is the first approach in the state of the art that takes advantage of the interactivity and neural networks. We call it deep interactive matching or eye matching. It allows users to interactively create the alpha mat using a few clicks or scribbles. Rely on a dense trimap, meaning that there is no need to create such a dense trimap. And you have a UI, basically, you can interact with the UI, and you can interactively and iteratively create a mask, an alpha mat, and you can refine this. And of course, we are trying to bridge this gap, as I mentioned, between the segmentation and between the matching to basically come up with a very unified model, a unified solution that could target both of these problems. And here is a very brief overview of what's going to happen. So we have an image in this case, and in our method, we basically give this image as an input to the network, and then we have a few clicks or scribbles where the foreground object is identified and the background area is identified. In this case, the red clicks are placed where the foreground object is or where the object of interest is, and then the blue clicks are where the background plane is. And as a result, this is a prediction of our model. And as you can see that the model is successfully capable of generating a very fine detail alpha mat. And here is a composition where we basically extract the object of interest based on the alpha mat that we have, and then we place it on a different background. In this case, we chose a very classic gray background, but this background could be any type of images, or it can be a video. And the method that we refer to as eye matching, a bit of a technical context on this side, is that one thing I have to mention actually is that the architectural design of this network is not really the novelty of this project. The novelty of this project is the alternating training strategy that I will explain later. But on the architectural side, the network follows a very standard unit encoder decoder architecture. The encoder is based on ResNet 50 architecture, and it uses the pre-trained ImageNet weights. We made some very small changes on the structure of the encoder based on the AlphaGAN, which is another state-of-the-art approach on alpha matching using the generative adversarial models, where we basically removed the strides from the couple of layers, added some dilation to layers. The decoder part of the network of our architecture, it's a very simple decoder. It contains 7 convolutional layers with 3 bilinear sampling and some skip connections. Our net training strategy follows the strategy that we try to estimate the alpha, we try to estimate the foreground, and we try to estimate the background as well. All the state-of-the-art networks, all the state-of-the-art classical approaches on alpha matching, they only try to predict the alpha. There's one big problem when it comes to predicting such a mask is something known as color spill. And when you predict the alpha, and when you try to extract the object from the background and place it on another background, you get the background color on the foreground area. And that's a very valid problem in most of the state-of-the-art software, such as After Effects. And the only reason that we are using and we are trying to predict the foreground and background is that we would like to get rid of that color spill problem. So we estimate the alpha, And then we try to estimate the foreground object as well, based on that alpha through the network, rather than simply extracting the foreground object using the mask that we have. And our training strategy is basically a novel training strategy, where for each epoch in our training process, for each epoch, we alternate between 3 different data sets with 3 different tasks. In each epoch of the training, for a certain number of iterations, we train the model on interactive alpha matching, and we train the model for a certain number of iterations on binary segmentation, and we train the model for a certain number of iterations for a matching with a dense trimap that we get from a predefined dataset. The interactivity during the training strategy is based on a script that we designed that mimics the interactivity of the human user, and it tries to basically place clicks on the image based on the errors that we get compared to the ground truths. And on the loss side of the story, we have tested a variety of losses, including the compositional loss, including the L1 gradient loss, Laplacian loss, etc. And at the end, we came up with a combination of these losses with a consistent weight. And one may ask, how did you come up with this composition? There is a huge amount of ablation study and experiments in this study. It's actually a very long paper, and we're planning to submit this for review. And as soon as the first draft for the review is ready, then we'll put it on archive. But there's a huge amount of ablation study. We had to test each of these individual combinations with weights and see how it affects the performance of the model. And at the end, we basically chose the weight that we have for our best model. For the evaluation part of the model, we tested the model on segmentation, and we tested it on the matching, classical matching approaches as well on classical data sets. For segmentation, we refer to classical benchmarks, state-of-the-art benchmarks, and we use 3 data sets known as GrabCAD, Berkeley, and SPD. The standard metrics to evaluate the segmentation masks to evaluate the segmentation for interactive methods are number of clicks that are required to achieve a certain accuracy. For this case, GrabCAD, the metric is number of the clicks that are required to achieve 90% accuracy, or Berkeley, number of the clicks that are required to achieve 90% accuracy. And because we wanted to follow the standard benchmarks, so we had to do the evaluation using the same metrics. And you can see here, eye matching in this table, we achieved the second best performing method in the state of the art. The first best method, which is mentioned in this table as Anonymous 2020A, is from the first author of our own paper, to ECCV 2020. So that paper is the best performing currently in the state of the art. And the eye matching paper, this interactive approach that I'm talking about right now, takes advantage of this paper 2020A and the second method that we have that I'll explain later. And here is just a brief graph showing the comparison of the mean IOU after n number of clicks. And again, it basically shows that how iMatching is performing against the state of the art. And it shows that basically we are the second best compared to the state of the art using the IOU score. And we also tested the method, evaluated the method using the standard alpha matching benchmark evaluation metrics, including SAD, MSE gradient, and connectivity of the alpha masks compared to the ground truths. We are presenting the results by the means of number of clicks, meaning that, for example, in case of SAD, after an average 4 clicks or 5 clicks, there is not much of an improvement. You may be able to achieve some very fine details in a very small part of the scene, but the difference is not going to be that much visible to the clear eyes. And this is where the state-of-the-art fails. And as I mentioned, state-of-the-art heavily relies on dense trimaps, where the foreground area is known, where the background area is known, and where the unknown area is predefined. And if we pass such a sparse input as foreground and background area by scribbles to the state-of-the-art approaches, this is what we are going to get for alpha prediction. And we also evaluated the method against state-of-the-art alpha matting approaches on alpha matting benchmark. And we use composition 1K dataset. It's a dataset provided by Adobe. And you can see again in this specific case, iMatting is the second best method, and the first best method is Anonymous 2020B. That's again another paper by the first author of this paper on the review, so we cannot mention. But if you refer to alpha matting benchmark, it's alphamattingbenchmark.com, if I'm not wrong, and you can see that the first method in the benchmark FBA, that's this Anonymous 2020B, which is of iMatting, this interactive approach that I'm talking about right now. And here is a very brief visualization of the results compared to the state of the art. The first column from the left is the input image and a few scribbles indicating the foreground area and the background area. And the last column is the prediction of the iMatting. For these images, we do not have the ground truths. These images are from a dataset known as diff2k. And the dataset, it's a dataset with high resolution images, and there is no specific annotation or labels for that dataset. We just wanted to see how the model performs on wild images that are not seen on the dataset. And here are a few high resolution results. And on the left side, we have the image, we have the scribbles where the foreground area is marked by red scribbles, red clicks. The background area is marked by blue scribbles. And on the right side, you'll see the prediction of the network, the alpha mask. And here we have another example. The UI that we design allows us basically to change the size of the clicks, to change the size of the scribbles. And this way you are able to achieve a very fine detailed and a very smaller regions of the scene. Thank you very much for your time, and that's all from my side. I'm more than happy to answer any questions if you have.
Okay. Thanks, Hossein. I don't think we have any questions on YouTube, actually, unless I missed that. And I'm actually already familiar with this research. So is anybody else here? Gul or Iacer, do you have any kind of observations? Maybe just
In
one
my
question.
case, yeah,
Sorry.
I was just going to say it's also the first time I'm hearing about the subject. It's very interesting work, but I'm really not familiar with even with the task. It's the first time I'm listening about it. Really cool work.
Thank you.
So the 2020 A paper that you mentioned, that's yours as well, isn't it, Hossein?
It's you know Marco, I think. It's from
Yeah.
the group, from Francois' group. Yeah.
Okay, right, great. So I mean, because when you looked at the dashed line for that, it seemed to pretty much outperform everything consistently, even with one click.
And so 2020A was designed specifically for segmentation tasks, and 2020B was specifically designed for matting. Our method is unifiedly trained for segmentation and matting at the same time.
Mm-hmm.
It's one unified model that targets both segmentation and alpha matting.
So maybe I have a newbie question. Can I ask?
Yeah.
Is there time for a question? Yeah. You showed some examples with images, and I wonder how well it would work with videos, which I suppose is like the main motivation for this kind of work, right?
And for videos, actually, we did not try videos for one problem. And for videos, you have to achieve a consistency in tracking the object of interest across the video. And to do that, we either have to use a certain mask tracking or initial segmentation and tracking or propagation across the video, or we have to individually apply this model to each frame of the video. To do that, we have to retrain or we have to fine-tune this model to achieve that consistency level that we get from the propagation. Or another idea would be basically to propagate the clicks. Instead of creating the mask, the user can draw the scribble in one frame, and then we try to propagate that, the scribbles or the initial mask of the foreground background that we get throughout the entire video, and then we pass that to the model and get the prediction of the alpha for each frame. But it's something that we did not focus on for this project. This project was solely focused on static images.
Cool, thank you.
Related
So
to that,
we have one question, and we've got praise from Yoris and Nishta, so take a bow for that. But Nicholas Parslow asks, do you use any data augmentation techniques?
We do actually. We do very basic data augmentation techniques in this specific case, which include rotation and cropping during the training phase. Other than that, there is not much of a data augmentation going on.
I was just wondering, are there data sets for matting in videos, or are they all focused on single frame?
There are actually data sets for matting videos, but very low quality data sets. And one big problem is that most of them are old data sets, and the very famous one is from Hollywood, and the data set is captured on green screen. And the ground truth is created using the classical software. And as I mentioned, the classical software, they have a problem known as color steal. So if you do the composition, even on those data sets with their ground truth, you see that the foreground object will have these greenish shades on the edge. And that basically will bias the output of the network, and we did not want to go towards that path.
We've actually got another question here from Mohammed Al-Rawi.
Yeah.
Feature is currently used in image editing programs, one of which is Microsoft Paint 3D. So I guess it's an observation rather than a question.
Sorry, I didn't understand.
So I think he's saying that this feature is currently used in image editing programs, one of which is Microsoft Paint 3D.
Mm-hmm.
So I presume it's not as good as your technique, but
there are a few classical approaches on alpha matting, but those are all mathematical approaches that you find in the state of the art. I showed in one of the slides here a group comparison with I can share my screen again.
Mhm.
I'll share my screen again and I will show the images. I think you can see the screen here.
Yeah.
So you can see, for example, the third column from right. That method is from 2005. So there are a few classical approaches on interactive alpha matting or matting generation, but the accuracy is not really high, and the computational time is very high. Given that some companies, they may have optimized the methods to increase the speed, but the accuracy is still low. So far, based on the alpha matting benchmark, these two methods are the best in the state of the art based on the standard metrics.
Cool. Okay, sorry, another comment from Mohammed. The one in Microsoft 3D is very basic and simple. The presented one is much more advanced. So there's high praise indeed. So you've got three of the audience praising you for that. So
yeah. No, definitely there are I think 3 state-of-the-art classical methods which are designed to deal with interactivity. But there are 2 problems. One is computational time, another one is the accuracy of the matching. In our case, the computational time for a high resolution image is for each round of getting the alpha mat prediction, it takes around 1 second or maximum 2 seconds, 1.3 seconds in average actually. And for each iterations. And so let's say if you want to have 10 clicks on an image to achieve a higher accuracy mask, that will take you probably between 10 to 15 seconds.
Mm-hmm.
To iteratively achieve an accurate mask. But classical approaches, you won't have this option.
Okay, right. Thanks for that, Hossein. And we're going to move on to our next speaker now, who is an ADAPT and DCU alumnus, Iacer Calixto, based in NYU at the moment. And he's going to talk about scene graphs for image captioning. And are they any good, or are they good enough for the task at hand? So over to you, Iacer.
Thanks, Declan. Let me share my screen in here. Can you see my screen? Or not yet? Yeah. Yeah. Okay. So, great. So my name is Iacer. Thank you for having me. And today I want to talk to you about this joint work with colleagues from KU Leuven, Victor Milewski and his PhD supervisor, Marie-Francine Meuns. And basically, we're interested in whether we can transfer learning from models that are trained to do scene graph generation, and whether we can use these models or reuse these models and transfer learning into image captioning models. So let's jump right in. In image captioning, just to refresh our memories, we have it's a very simple task where we have an image and we want to generate a description, a textual description for this image, a sentence. And basically, all image captioning models that perform reasonably well apply transfer learning somehow. And in here, in this slide, we have two examples. One example, like you have this number 1 and number 2 in here, and they all use transfer learning from different tasks. Example 1 uses transfer learning from an ImageNet image classification model. Basically, the idea in here is we have a convolutional neural network and very deep, usually. In this case, it's probably a VGG or a ResNet architecture. And this model is trained on image label pairs, where the label is 1 out of 1,000 possible labels from the ImageNet dataset. And you train the model to, given an image, classify the image with its label. And then after you train that model, you just reuse the CNN, the image encoder, and you plug a decoder on top of the model and train the model now on image captioning data, where you have image and descriptions as your training data. That's model 1. In model 2, the main difference is that models are pre-trained. This model is pre-trained on object detection. So the task of object detection is you have an image, and for this image, you want to predict all bounding boxes that denote objects in the image and label these bounding boxes with the object class. And in this particular work, authors use transfer learning from a faster RCNN architecture. The faster RCNN is the object detection network. Then they just reuse this image encoder backbone and plug a decoder on top of the model to train image captioning model. And this is called the bottom-up, top-down baseline. We're gonna talk about it in a few slides. But yeah, so I hope I managed to motivate you to the main ideas we want to discuss, which is, like, we know that transfer learning from CNNs trained on ImageNet classification and object detection work. And they work quite well. Both those papers we discussed were state-of-the-art at the time they were released. And now we're interested in whether using scene graph generation models, transferring learning from CNNs trained on scene graph generation, can lead to even better results. So a bit on scene graph generation. So scene graph generation is a relatively newer task where the idea is, given an image I, we want to predict a scene graph G, which is like a scene graph that describes the image or represents the scene in the image. And a scene graph is, for the purpose of this talk, it can be a bit more complicated than that, but we can simplify the idea and say that scene graphs are graphs with vertices, set of vertices that denote objects in blue, in the right in here, and a set of edges that denote relations between these objects in orange, also in the right in here. So we have an image. This image goes through an object detection pipeline, actually, and we predict bounding boxes for the objects in this image. This is like classical object detection. And then we have a graph inference model that's going to label the objects, but additionally, it's also going to predict the relations between pairs of objects. So ideally, since there is more knowledge involved in such models, like we're adding relations. If we remove the relations, we're pretty much doing object detection. But by adding the relations, we should be able to get more accurate representations that should transfer better. But that doesn't seem to be the case. And that's what led us to ask this question. Like, can we use scene graphs, namely predicted scene graphs, to improve image captioning? And this is basically a dialogue with some papers that in the literature, in the very recent literature actually, that have answered this question with a yes. But I think the results we're going to show is like that the answer is either no, or most likely it's at best ambiguous. And according to some metrics, we can improve. According to other metrics, not as much. Now, let me just show you the model architecture, the overall model architecture we're proposing here. So this is an image captioning model, right? On the left in here, we have an input image, and in the right, we have a 2-layer LSTM decoder that's used to generate the caption for the image. So the image goes through two, let's say, pathways, data or information pathways. In the first branch, we feed this image into a pre-trained object detection network, faster RCNN in our case. Then bounding boxes are predicted, and we collect features for these predicted bounding boxes. These are shown in red in here. We do the same with a pre-trained scene graph generation model on the top branch, where we use the iterative message passing pre-trained scene graph generation model. And we're showing object nodes in green, and relation nodes in blue. We collect features for these as well, and these are shown like in green and blue, just to the right. We optionally have an additional graph layer that's used to update the graph hidden states, namely the object and relation states. And we use either a graph attention network or a conditional graph attention network, which is like a minor novelty in this paper, which is a modified graph attention layer, which is conditioned on the state of the decoder. So you see an arrow from LSTM1 going into CGAT. That means that when we update the states of the scene graph, we're taking the decoder state into consideration. So that if we're generating the first word, we want the states, the scene graph states to reflect that. So we end up with two sets of features from scene graphs and from detected objects from two different retrain models. And then we study different attention mechanisms to try and collect these two. One simple trivial attention would be using a flat attention, where we simply attend independently to both feature banks, or we could have a hierarchical attention, where we either attend first to the objects in red, summarize them, and use this summary to select the scene graph states, or do it the other way around. We first select the scene graph states, get a summary vector, and then use this summary vector to select the detected objects. And this goes into the second layer of the LSTM that generates description word by word. Okay, so very briefly, a graph attention layer or a graph attention network is a graph neural network, very simple one, basically the idea is if we have 6 nodes, H1 to H6, and we want to update the state of node H1 into this H1 prime, we simply have an attention mechanism that collects the state of the entire graph or the subgraph connected to H1, uses attention mechanism, multi-head attentions in this case, and either concatenates or averages the results, and this is what becomes the next state of the node H1. And you can see that this graph attention network takes knowledge from the entire graph, but it can't condition on anything outside the graph. And ideally, we want to see whether that would help or not. So in this slide in here, we have in the left in here, this is the illustration of a CGAT layer or a conditional graph attention layer. So let's say we want to update the state of the node man in the scene graph. The nodes that are used to compute the new state for man are the incoming nodes. That's just a definition. And in this case, we have sun above man and tree right of man. We collect these states in the middle in here, and then this is what is used to compute an updated state for man. The main difference is that we use an additional or external query vector that affects the results of this operation. And this query vector, as I already mentioned, is the decoder hidden state. And so it's the updated man, it's going to change depending on the word you want to generate. Okay, so now I just wanted to go on and discuss a few results, just to give you an idea of what's going on. Here we're showing 4 metrics in the columns. We have Blue 4, Cider, Rouge L, and Spice. These are all metrics used to evaluate image captioning models, where arguably Cider and Spice are the more important ones. Of course, we can discuss that if there are any questions. But there is the bottom-up, top-down baseline first, which is a model that only transfers learning from object detection networks and not from scene graph generation models. Okay, the next 2 models are Cascade and No More Say Less, KMSL. And these 2 models they do transfer learning also from scene graph generation models. And the 5 last entries are our models. The flat attention, the hierarchical attention with the predicted objects first, hierarchical attention with the scene graph first, and plus a GAT layer and plus a conditional GAT layer. So I guess the first thing, I know it's a lot of acronyms and a lot of numbers, but I guess the most important point in here is that although there seems to be improvements for most of these metrics, this improvement is either small and or not as consistent as we would like. For example, with Spice, models either are around the same ballpark as the baseline or they are a bit worse. Ideally, we would like to see something a bit more consistent. So that led us to the discussion of, so maybe there's a problem with the scene graphs. And then we decided, okay, so for the scene graphs, we actually have this metric, recall at 100, which measure the quality of the scene graphs for a subset of the data we have. So the higher the recall at 100, the better the scene graph. And we decided to compute recall at 100 for our predicted scene graphs. And this is what we found. So namely, a large majority of the scene graphs is very noisy and very low quality. So that could be affecting negatively in the downstream task, right? In the image captioning pipeline. So then we decided, okay, so what if we train, if you simply use subsets of the scene graph that we know the quality. So we decided, so actually there are many more results in the paper, and the results are actually even a bit more nuanced than the message in here. But the overall message is, if we use a model, actually, if we evaluate our models only on average, on images that have average quality scene graphs, the baseline bottom-up, top-down outperforms the other models. But if we only use the images that have high-quality scene graphs, we actually observe the opposite happens. So our models that use scene graphs really outperform the baseline consistently. And the improvements are actually a bit more pronounced as well. Namely, it's not such, because usually we'd see like 0.5 improvements, 0.7 improvements in two metrics, and maybe it's about the same in the other metric. In this case, the improvements are more pronounced and all metrics agree. So that kind of indicates, I would say, that there might be some room for improving captioning, given that the scene graphs we have are of high quality. Okay, so now I'm gonna wrap it up. So the main takeaways I think I would like to finalize with is, first, I want to give you a few more data points in trying to consolidate knowledge into this new line of research, which is using scene graphs for image captioning and transfer learning for vision and language more generally. I would say that currently scene graphs do not seem to be good enough to consistently improve captioning. This is contrary to previous findings in previous papers. So I hope to really start this dialogue and that further research can continue along this line of work. And also that a positive outcome is that it seems that high quality scene graphs can boost image captioning performance in our experiments by up to 3.3 CIDR. So that really shows that there might be room for improvement. And yeah, that's also pointing towards a direction of future research, like better scene graph models, or maybe filtering out, trying to filter out noise from scene graphs to try to improve image captioning. And yeah, there is a link to the preprint. It just went online yesterday. And yeah, I think that's pretty much it. And now I would be happy to take any questions you might have. Thank you. Let me go back.
I do have one question.
Yeah.
Thanks, first of all, for the presentation. That was
Sure,
very
you're
interesting.
welcome.
Have you thought about, well, maybe you have, but how much do you think incorporating something like semantic segmentation to increase the accuracy of image captioning? Well,
Semantic segmentation.
yes, meaning that you identify the objects which are present in the scene.
I actually haven't played with semantic segmentation, to be very honest.
Okay. The idea would be, for example, you can get a map of the image that tells you that, okay, here you have a table, you have a chair, and maybe you have a bottle in the scene. The question is, would that information help during the process of generating the caption of the image?
Yeah, that's actually a good question. I wouldn't be so sure whether it would help. Like, I wouldn't be inclined to say yes or no. It should or it shouldn't. The main idea of looking at the scene graphs is because there is actually some additional, let's say, knowledge in the graph that there isn't only in the objects. In theory, when you have a semantic segmentation, you would get maybe a crisper view or a crisper take on the objects, but still let's say the data is still the same. But yes, by my intuition with the scene graphs is that by having also the relations between objects, which are very hard to predict, maybe that could be an extra amount of information that could make a difference at the end. But having said that, I think Yeah, that should be definitely doable. One thing that I didn't mention in my talk is that most state-of-the-art or the best performing image captioning models nowadays apply some kind of transfer learning from object detection networks. And they don't transfer learning from scene graphs. And that's also one of the motivations why we wanted to conduct this study, to see why. Yeah.
Very good. Thank you.
Sure, you're welcome.
So we have a question on what do you think the bottleneck is to producing better scene graphs?
The bottleneck.
Yeah.
Yeah. I mean, it's a new it's a new area of research, right? Like relatively to object detection, and with any new area of research, it really takes time. I guess the first short and cynical answer would be like it just takes time to fine tune your hyperparameters, and it's like a collective effort, right? Like when neural machine translation became a thing and research groups around the world started doing neural machine translation, like I think it took some time until people found what's the right combination of like trivial or mundane things like the nonlinearity or this hyperparameter and so on and so forth. So I think on the one hand there is that, I would say maybe we haven't tried for long enough to come to really good hyperparameters. But on the other hand, the relations are something that are very hard to predict. Their objects should be we get a high quality object detection by tuning our networks a lot. But I think for relations, for predicting relations, it's not as straightforward because many of these relations are very low frequency relations, and it's also not it's more like a vision and language problem and not so much a vision problem per se, because many times it's not something about the image only. It's really about common sense knowledge, and it's world knowledge, and it starts to involve like a lot of inference steps that are hard to make solely based on the image. So you really need like more things at play, maybe more knowledge sources, or yeah. I hope I kind of answered the question.
How are there many graphs for a single image, or how are the data sets constructed for scene graphs?
Mostly there is the visual genome data set, and it has, I think it's 80,000 images and scene graphs. So it's not like massive data sets. That's also a bottleneck. Like the data acquisition for training data is definitely also a bottleneck. And the annotation quality is also a bottleneck because in principle, scene graphs are an exhaustive representation of the scene. And many times an image has a scene graph, has an associated scene graph that kind of doesn't really models some of the objects in the image. So there is also, yeah, there are many issues actually. And the data is definitely an issue. That's very well remembered.
Another couple of questions from John. He says, thanks. Oh, he may have answered this, but thanks. I was going to ask if you think the current scene graphs are strongly connected to the actual images, or is it just based on a prior?
Yeah.
Based on detected objects? E.g.,
yeah,
if you find a cat, a mat, I'm sure the relations sit and is the main.
Yeah, exactly. Yeah. I think I might be unfair if I answer this question saying like that current models don't do that. Also because, I don't know, scene graph generation models are being released like on a weekly basis, pretty much. It's a very active area of research, but that's definitely something that has to be addressed. Like improving upon a model, like let's say as simple as this, as a model that considers this prior and tries to improve on that, is very hard. It's a very hard problem.
And then I have one more question. So I think in image captioning, there can be problems where models will generate repeated text to become
Right.
specific. Is that somewhat solved by having a structure of the scene graph? Or
No, I wouldn't say necessarily. No. Yeah, with image captioning, like, I think if your model is well tuned, you shouldn't have this kind of problems. In assuming like you have enough data to train the models, right? But I mean, ideally, we would expect the scene graph to lead the model to better describing relational terms or relations between objects, right? But then we don't really know to what extent reference captions already include these relations, object relations, if people pay attention at these things when they're describing an image. So yeah, I think there are like many things that can be done in this area. But about the repetitive patterns in the description, I don't think it should help. Maybe just because it's more data, it might. But I think it's really a matter of having enough data for the model to learn to do it right. Yeah.
thank you very much. So next up we have Bill.
Yeah.
Thank you.
Let me share my screen. Just tab. Is it working now?
Oh, yeah. Perfect.
Okay, perfect. Hello, everyone, and thanks, Matthew and Declan, for having me and for the introduction. I'm the machine learning engineer at CaliberAI, where we tackle with the defamation and toxicity content detection in the publishing sector. So I will start with the outline. So I will give a brief definition of defamation and toxicity. Then I will continue with some illustration of the tool we have. And I will give a brief introduction of the classification methods that we find useful for our tool. Then I will introduce again ensembling machine learning models, and we'll finish it with our approach. So what is defamation and toxicity? Defamation is the publishing or uttering of or anything that could have the effect of injuring someone's reputation or could cause someone to be lowered in the opinion of other people or right-thinking people. A given statement should do a genuine damage to someone's business interests, career prospects, personal family life. As an example, how can a woman like this be put in charge of somebody's finances, or he's known to hold an extremist views or defamation examples. The reason is that people will likely to question the quality of their work or professionalism, and will likely to avoid trusting or hiring them. And other criteria for defamation can be unproven accusations of criminality and damaging allegation from an anonymous source. Whereas toxicity is actually targeting people on the basis of their identity. This includes, but not limited to, homophobia, xenophobia, racism, misogyny, Islamophobia, or regular gender stereotypes, and generally aimed at the disabled ones, the traveling community, or the religious minorities. And the language is harsh, like violence, threatening, or insulting. Defamation and toxicity are a challenge for publishers, editors, and other disseminating news and information tools. These problems are currently addressed by a costly combination of sub-editors and lawyers. because of the diminishing revenue that is assigned to these resources and capabilities, the likelihood of getting costly error is increasing. So this is where actually CaliberAI takes part. We as an ML company aim to build NLP-based tools to assist digital content creators like publishers, editors, and other professionals in the pre-publishing detection of potentially defamatory or toxic speech in order to reduce the risk of publishing such materials. While AI algorithms have become more and more prevalent, they are unable to help people understand what kind of features they're focusing on. In other words, explainability and interpretability are still considered as the flaws of these algorithms. So to assist publishers in revising their materials, we provide an explanation feature that returns which words or phrases are associated with defamatory and toxicity. Algorithmic bias, also known as AI bias, represents an unfair outcome in this area. So for instance, showing qualities that give off impression of being sexist, supremacist, or in any bias can be problematic. So this bias can emerge due to many reasons, such as the way the data is collected, generated, or is trained. So we intend to reduce bias with respect to gender, race, sexuality, and other human traits by neutralizing the data we are generating and collecting, as well as the way we are implementing our algorithms. Let me show you a couple of illustrations from our tool. So this is the landing web page for our tool, where you can type in a sentence in the center. And there are a couple of examples in like below. If you don't have anything in your mind but would like to try out the tool to have a better understanding of the returns. And we have a demo page like providing even more examples for these sentences. And this one is defamatory and toxic examples. The highlighted words and phrases indicate the important words in a sentence that are associated with the classification. So turns a blind eye is very important in this example. And also the size of these phrases represent the numerical value or the size of these attention weights returned by the algorithm. And the same applies for the toxic example. Shame, red hat, and suitability are important words that are correlated with the toxicity. So this is the test page where you can add a heading and body paragraph like you would do as a journalist or a publisher. We wanted to give the working space like to our users. And for this one, after we install the Chrome extension, we need to activate the extension actually by clicking the icon on the right hand side, right top of this page with the CaliberAI icon. And then when you type in a sentence and ends with a punctuation mark, the algorithm processes this sentence and returns the classification. And not to be distracted, you can close this box actually and get the all sentence classifications at the end. This is another example for an article from Breitbart. You can have classifications from an article when you read something. And now let me continue with the existing approaches for text classification. And the first one is the hierarchical attention network for the document classification. The idea behind this network is that words make sentences and sentences make the documents. The attention network for words gets weights corresponding to each word. Then it aggregates the representation of those words to form a sentence vector. For instance, this S2 is a sentence which is formed by the word vectors from the W21, W22, and so on. They are all sent through an LSTM, bidirectional LSTM-based network to get the word attentions, and then it retrieves the sentence vector based on that. Then the same applies for the transformation from this sentence to the final representation, which is the document classification. Since there are two levels of attentions, it is called hierarchical. This is a great idea, but it is insufficient to detect subtle innuendos, such as neutral examples with negations or defamation by implications. So we jump to the second model, which is recursive neural network, which are general form of recurrent neural networks. When a sentence given to the network, it is parsed into a binary tree, and each leaf node corresponding to words is represented as a vector. These networks will then compute the parent vector in a bottom-up fashion using different types of functions like softmax, sigmoids, or hyperbolic tangent, depending on the problem we're dealing with. The parent vectors are used as input features and given to the classifier to be trained on. This one is actually successful in carrying the effects of negations from the words from the leaf nodes till the root nodes, but the computational power that is needed to parse the sentences and process them is extremely large. And then we continue with the ensemble models. Probably most of you must have heard, read, or used in one of your algorithms, but for those who don't know, I wanted to just give a small information about it. Ensemble models actually combine decisions from multiple models to improve the overall performance. So it uses the strength of each classifier and get rid of the weaknesses. When we get the predictions from each classifier, we use these ones as inputs for the meta classifier, or like the ensemble model, and we get the final prediction based on that. So it creates a more stable and robust model using the power of each model. And you can see the whole system architecture here. And it consists of data generation, expert data verification, feature engineering and model development, and training these models with the training data, and getting user feedback from our trial partners, and improving the algorithms with these feedbacks. So in the data generation parts, each week, our data annotation strategists invent defamation examples based on building blocks provided by our computational linguistics expert, Alan, and collect toxic data from blogs, forums, and social media platforms. Then each of these sentences is verified by our experts. Then the feature engineering and model development part starts, where we apply lemmatization, post-tagging, and dependency parsing, and other NLP methods to get the input for the models. We then convert them into embeddings, encodings that will be assigned to their feature vectors, which we are using globe embedding at the moment. We then have 3 models ready for the deployments, which are an LSTM-based recurrent neural network with attention mechanism, a recursive neural network, which is based on Stanford's tree-bank model, and a statistical baseline model with random forest classifier to obtain a baseline accuracy separate for defamation and toxicity. After getting a feedback from our users, we do research about the underlying reasons and pitfalls of the models, like which misclassification stem from, and then improve the existing models to increase the accuracy. And we do the same process over and over again, but of course we are facing with challenges. The first one is definitely the limited training data. We are gradually increasing the data sets, but we are still far from the optimal amount, which can be millions of rows that is necessary for neural networks to work perfectly. The second one is the existence of gender stereotypes in globe embeddings in which certain professions are associated with specific gender. For instance, the word embedding of receptionist is closer to that of women instead of men. And the third one is the subtle innuendos. Actually, is the hardest one, in my opinion, to detect even by humans, and the most significant one for us in the short term and in the long term, as in law cases involving defamation by implication, the actual malice standard probably provides an even greater hurdle than in a typical defamation case. The milestones we would like to achieve in the future, because global embeddings are context independent, they provide a single word vector irrespective of the context. Not to miss the meaning or representation of these words within different contexts or the users users would like to get, we will switch to pre-trained transformers such as BERT, as it can generate different word embeddings for a word that captures the context of that word. As seen in the CaliberAI tool, we show the defamatory and toxicity classifications, and we want to develop an alternate phrasing, in other words, autocorrection feature to help users edit their text in real time without getting flagged. We will develop an automated user feedback mechanism that will improve the model's prediction in a systematic way. With the contextual classification, we will be able to understand and classify texts in the context the users work in, like from sentences to paragraphs or to entire documents. The last but not least, we will provide multiple product paths for the integration of our technology into the user's workflow. For instance, browser extension like Chrome extension or Firefox extension, website, API, content management system, and software development kits. That's all I would like to talk about. If you have any questions, you can reach out to me by this email address.
Do you have any
Okay.
questions? Or, one thing I wonder about, is there much difference between cultures over what is defamatory or toxic? That would it.
Sorry, I did.
Is there much difference in what's considered defamatory or toxic in different cultures, like between the US and British English, or?
It's actually like in the expertise of my colleagues, like defamation. There's absolutely a cultural difference for defamation and toxicity, but from the law point of view, there are some definite definitions for each of these terms. So there are ground truths about classifying a sentence or annotation. Defamation and toxicity is pretty much have clear boundaries.
Can I ask a question?
Yeah, of course.
Yeah, it's a kind of a follow-up question, I believe. I'm interested, like, in the training data, like what's the order of magnitude you're talking about, and also, like, of course, you have to annotate this training data with like all these nuanced definitions, and how much subjectivity is there in such a task? Like, you probably have to make decisions of annotation guidelines, which can be more or less subjective. I don't know, because I never worked with these specific topics, and it seemed there might be a lot of room for interpretation, or but you said no, right? Like that was exactly what you were saying, I suppose.
About the training data, actually, we have over 33,000 number of annotations at the moment. So it is a pretty small data set to use with neural networks. And as we increase the number, the neural networks are increasing their powers, actually, all of the models. And about the subjectivity, we would like to get rid of this bias or subjectivity as much as possible. To achieve that, our annotators are creating these defamation or like collecting these toxic examples, and then another like totally somebody totally expert in the area is actually verifying the annotations. So we are double checking just to make sure we are on the line and not to have any like legal issues like in the future.
Thank you.
Are you able to pull examples from case files in law where there are examples of legal implications for utterances, or?
Actually, I had an example from the US law cases about the defamation case, but I removed it from the slides because of the timing issue. But there are like every day we find like hundreds of these legal cases that are associated with defamation cases, and I think the hardest one is to like prove their existence or non-existence, because somebody can accuse someone of doing something over in Twitter, and that person like you are thinking about whether this person did that or didn't do that. So I think like legal obligation and liability is very important in that regard.
And are examples from is it struggle having formal text versus less formal text in social media, or how is that represented in data?
Actually, we're creating these defamation examples based on these building blocks that journalists or publishers would use. So they're more like formal sentences. Yeah.
Thank you very much. Very interesting.
Thank you.
Yeah, thanks everyone for presenting.
Yeah, thanks for having me.
Thank you.
Thanks.
Thank you.
Bye-bye.
Bye.
Bye-bye.